Hi everyone, I'm Leo, and today I'm going to tell you a little bit about my robotic arm. What you see in front of you is the arm itself, both in the physical world and in simulation running the same calibration script. In this video, we'll be talking about how I designed and built the hardware, how I wrote the firmware, and also how the inverse kinematics controls works on this robot. So let's get started. Okay, so let's start with the hardware. At the beginning of the design process, I had to find out exactly how much torque the servo motors could handle. The data sheets honestly were kind of useless because they only gave me the stall torque, which is basically the max amount of torque it would take such that you would completely stop the servo motor. But the thing is, um, at that point, it would already be too late. The arm would already be useless way before that, so I had to find out what like the max continuous torque was, the sort of torque that it could exert as it was moving, and that required some tests, and I also found out that the continuous torque is way below, uh, maybe like a third of the stall torque, and after that, after finding the torque, I was able to find the rated load of the robotic arm, which was around 380 grams. So, with that in mind, all that's left to do on the design part was to draw some shapes with screw holes in them and design them in CAD. Around, yeah, 10 custom parts in the robotic arm. This is the building process, and here are some tips that I would give to people who also want to build the robotic arm, which is to build, which is to make sure you buy high quality servos and steppers. I bought pretty low quality hobby servos, and the problem is that they're not precise enough. The resolution isn't that great, so you're gonna give you're gonna get like slightly different ranges for the same servo motor, like 0 to 185 or 0 to 180 degrees for the same two models of the servos. So that kind of sucks. It really limits what you can do on the control side. Um, yeah, make sure you think about wire management as you're designing, um, and then make sure you test every motor. Uh, it really sucks if you've already assembled your arm and then found out that a motor isn't working. And also, yeah, make sure you know exactly what the range of motion of the servos are, uh, and record it down somewhere because this is going to be extremely important when you try to simulate the robotic arm, where you have to write in the joint limits of each motor, and also when you try to control the robotic arm, so you know which angles lead to which location. So I finally got around to doing the wire management. Here it is. And for the firmware, um, what it is, it's a Python script that communicates through the USB serial port with sort of 6 joint commands in degrees, um, and then an Arduino script then reads from the serial port and commands the motors accordingly. And here's an example of that sweep.py program running on the robot, which was also the calibration script I referred to earlier. So in this program, the arm was just commanded to go from the minimum range to the maximum range. Okay, so let's talk about inverse kinematics. Inverse kinematics is basically all about given a pose in 3D space, uh, what are the correct joint angles to get the arm to that location? And for a 6 degree of freedom system, meaning a robotic arm with basically 6 motors, um, you sort of have 2 ways to go about it. The first one is with geometry. Um, it's possible, but pretty messy. And I didn't want to draw that many sines and cosines, um, and and torment myself. So I decided to go with the second way of doing inverse kinematics, which is with an inverse solution. Um, what that does is it turns the control problem into an optimization problem, and it does that by um, trying to minimize sort of the error between your desired velocity and the current velocity of the robotic arm's end effector. We'll go more into depth into that later, but another great thing about this iterative solution is that it generalizes to any degree of freedom, at least for serial manipulators, meaning ones that ones that form a chain instead of a loop. Okay, so, but before I talk more about the inverse kinematics, I need to make sure I talk about how the computer computes the end effector pose given the joint angles. So this is the other problem, the forward kinematics problem, where you know the joint angles, and then you have the end effector pose. And this is this is something that it's much easier, because it just becomes linear algebra at the end. Um, and what I have here on the screen is I have sort of this variable x, and what this is a transformation. You can think of it as a rotation matrix, and then a translation in the rotated space from this link P, which stands for parent, to this link C, which stands for child. And then it's parameterized by this vector Q. In our case, that would be the 6 joint angles. And all the transformations would really only be reading from one of the joint angles, depending on what joint it is. But just conventionally, we would just put in the vector Q to indicate it. So this is the transformation for a single joint of the robotic arm. What you see here is that you have a transformation from the center of the link, the parent link, to the frame of the joint parent, and then that joint parent would basically be touching the child parent in the revolute joint. Okay, so sort of like if it's rotating around the Z, it would kind of be like this, where this could be the parent, this could be the child. And then that would be parameterized by the joint angle. So this could be moving. This is not a static transformation. And then after that, you compose it with the joint child to the child center frame to bring the transformation to the joint's sort of center position. And then together they form, this transformation of a revolute joint. And if you compose a bunch of these joints, you basically get the transformation from like the base of the robotic arm to the end effector of the robotic arm. Or in other words, the forward kinematics solution to this arm. I also have this extra term at the front. So it's WXL1, meaning it's the transformation, the rigid transformation from the world frame to the base link, basically, of the robotic arm. What this does is that basically when you define an object in 3D space, you typically define it with respect to the world frame, not from the frame of the base of the robotic arm. So that extra transformation accounts for that. Okay. So now that we covered forward kinematics, let's talk about how differential inverse kinematics works. Differential inverse kinematics is just one way of doing it, and it does it by matching the desired velocity with the current velocity of the robotic arm, which is why it's called the differential inverse kinematics algorithm. And before we look at this algorithm, let's just talk about this at a high level. So the best way to go about this is to first understand what the Jacobian of the end effector is. So the Jacobian is basically uh, the matrix that transforms the derivatives of the joint angle of the robotic arm to the derivative of the pose of the robotic arm. So from those six joint angles, you get a vector, you take the derivative of that vector, you multiply by the Jacobian matrix, and then you get the derivative of the x, y, z, yaw, pitch, and roll derivatives. And then once you have that, you want to make sure that it's similar. You command the. Okay, wait, actually, first notice how this is a linear relationship. So it's q dot multiplied by the Jacobian matrix. So this linear relationship means that, well, we can use least squares optimization to find the desired q dot that brings us to a desired pose velocity, which means if we have j multiplied by q dot equals to the desired velocity, so let that be v, then we can take the pseudo inverse of j on both sides, which gives us q dot equals to the pseudo inverse multiplied by the desired velocity, which gives us the exact q dot we need to go in the direction of our desired velocity. So that's how it all works. And in the algorithm, I also added a damping component to the movement, and the reason why is because near singular. Okay, so at some positions of the robotic arm, for example, when it's straight like this, it doesn't make sense for the arm to move directly in the negative. Let's just call this the x-axis, so the negative x direction. It can't move in that vector instantaneously, and that is what we call a singularity, right? Because it's the joints are locked. So that's what we call a singularity. And in that case, the Jacobian singular values would explode. Or sorry, the pseudo inverse of the Jacobian would have singular values that explode. And we can't have that. So that's what the damping term here is for. It basically penalizes the Jacobian from behaving that way and allowing us to have values that make sense even in these singular positions. And you also might be asking, okay, so this matches the velocities. How do we go from a desired position, a desired pose, to a velocity? Well, in that case, I just scaled the error by a gain, and that basically was the desired velocity. Okay, so now that we talked about the inverse kinematics algorithm, I'm just going to demonstrate it. So let's see. First, let's take a look at oh yeah, the arm's called Armathy. Tests. Okay. So this is a test program where I was seeing if this program worked. Yeah, and you can sort of see here how the current pose roughly matches the target pose, which means, yay, it does work. Yeah, and it tries to get closer at every iteration. Yeah. So that's that, but let's take a look at a more a more visually appealing demonstration. Unfortunately, that one does not work, and I don't know why. But I'm just going to show it anyways because it involves the simulation of the robotic arm. Okay, so ROS2. Wait, no. And this morning, the simulator also decided to break for some reason. Isn't that just wonderful? Okay. Anyhow, we'll try to make the most of it. What I have here is a panel in which I can enter my target pose. I can also modify it just by a little bit with keyboard commands, and then through ROS2, that program communicates with my now weirdly broken simulator for some reason, and moves the end effector. So as you can see, yeah, it does move. Right now I'm trying to move it down, but it's not cooperating. So there's still some issues with my inverse kinematics algorithm that I am not sure is what the cause is. But I just wanted to give you sort of at least an update on how this project is going, and I hope you got something out of it.